Welcome to our explanation of Bayes' theorem, one of the most important concepts in probability theory. Bayes' theorem allows us to update our beliefs about events based on new evidence, making it a fundamental tool for statistical inference and machine learning. Before diving into Bayes' theorem, let's quickly review some basic probability notation. We use P of A to denote the probability of an event A occurring. The notation P of A given B, written as P of a vertical bar B, represents the conditional probability, the probability of event A occurring given that event B has already occurred. Now, let's introduce Bayes' theorem. It states that the probability of event A given event B equals the probability of B given A multiplied by the probability of A divided by the probability of B. This powerful formula allows us to reverse the conditional probability and update our beliefs based on new evidence. Let's break down this formula to understand what each part means. P of A is called the prior probability, our initial belief about event A before considering the new evidence B. P of B given A is the likelihood, the probability of observing the evidence B if A is true. P of B is the marginal likelihood or evidence, the total probability of observing B under all possible scenarios. And finally, P of A given B is the posterior probability, our updated belief about A after considering the evidence B. We can also expand P of B in the denominator using the law of total probability. If we have a set of mutually exclusive events, a complement, then P of B equals P of B given a times P of a plus P of B given a complement times P of a complement. Let's visualize Bayes' theorem using a probability tree diagram. We start with the initial split representing our prior beliefs about event A P of A and P of not A. Then from each branch, we show the probability of observing evidence B. The probability of ending up at each final outcome is the product of probabilities along each branch. Bayes' theorem helps us go backward. If we know we've observed B, what's the probability we're on the A branch versus the not a branch? Let's apply Bayes' theorem to a classic example, medical testing. Suppose we have a medical test for a disease that affects 1% of the population. The test is 99% accurate, meaning it correctly identifies 99% of people with the disease, sensitivity or true positive rate. It correctly identifies 99% of people without the disease, specificity or true negative rate. If someone tests positive, what is the probability they actually have the disease? To solve this problem, we need to find P of D given positive test. Let's define our variables. D represents having the disease, and plus represents testing positive. Applying Bayes' theorem, we get P of D given positive test equals P of testing positive given D times P of D divided by P of testing positive. Expanding the denominator, we get P of testing positive given D times P of D plus P of testing positive given not D times P of not D. Now, let's substitute the values we know. The sensitivity P of testing positive given D is 0.99. The prevalence P of D is 0.01. P of testing positive given not D is the false positive rate, which is 1 minus specificity, or 0.01. P of not D is 1 minus P of D, which is 0.99. Let's calculate the result. The numerator is 0.99 times 0.01, which is 0.0099. The denominator is 0.0099 plus 0.0099, which is 0.0198. Dividing, we get 0.0099 divided by 0.0198, which equals 0.5 or 50%. This result might seem surprising. Despite the test being 99% accurate, if someone tests positive, there's only a 50% chance they actually have the disease. This is known as the false positive paradox, which occurs when testing for rare conditions. Let's visualize this with a population grid to make it more intuitive. Imagine a population of 1,000 people. Since the disease prevalence is 1%, 10 people have the disease, and 990 people don't. Of the 10 people with the disease, the test correctly identifies 99%, or about 10 people. Of the 990 people without the disease, the test incorrectly identifies 1%, or about 10 people, as positive. So out of 20 total positive tests, only 10 are true positives. That's exactly the 50% we calculated using Bayes' theorem. Bayes' theorem is a powerful tool for updating our beliefs based on new evidence. Remember the key components: the prior probability, the likelihood, and the evidence. This theorem has wide applications in medicine, science, law, machine learning, and data analysis. The counterintuitive results we saw in the medical testing example demonstrate why understanding conditional probability is so important, especially when making decisions based on test results for rare conditions. Thank you for learning about Bayes' theorem.